Now, there are some reactions in chemistry that we can't do or haven't worked out how to do, but there are other ways for us to get them out from A to B, such as going from A to C to D to E. And so the clever thing is, as long as it all adds up like a simultaneous equation, so you can't have energy or matter lost or gained, and then you can still know what the enthalpy of the reaction is by adding them all up, and it will actually equal the same thing. Okay, so delta H will equal the sum of all 1, 2, and 3 from this diagram here. So have a look at how it works. We'll go to some problems. And this is also very good for solving problems with redoxes, and we'll do Born-Haber cycles as well. So the whole solving simultaneous equation things is quite cool that it works for chemistry. So let's just say we're trying to get to this and we can't do it. We don't know how to get the enthalpy for that, which we do know. But anyway, but we do know how to do these equations and we know what they are. So what are we doing is we're just going to add them together to make them look like this, and then we'll get the correct enthalpy. Now, oxygen here is on the wrong side, so this one will need to get reversed, and this one here is on the correct side. Once we reverse it, these will cancel out, and this will add up to 1, which is what we want, and these are already in the correct form. So first just... as a basic rule, first just try and reverse it, and if you need to, you might have to times something by 2 or 3. So I've grabbed this first one here that I knew I had to reverse, and I've reversed it. Make sure I've reversed the sign, and then you just add them together. So if you add these two up together, it gives minus 939.5. Just make sure the reaction works. So I grab all of these. That adds up to 1. There's the C, there's the CO, there's the CO, there's the CO2. These are on both sides, so they cancel out. And then I can just bring them down, and it looks exactly as the one up here. Okay, so the answer is minus 393.5. Okay, so just trying one where we're doing the timesing out as well. So let's just say we can't do this, and we want to know what the enthalpy for this is. But we can do these equations. So the carbon dioxide is on the correct side. The sulfur dioxide is also on the correct side. And this one here, CS2, is not. So we have to reverse that one. And then we've still got a 2 here. So we're going to have to times that one by 2 as well. So just rewrite those ones out. So I kept the first one as it is. The second one I've times by 2. So I've done that underneath. I don't need that anymore. And then I've reversed the other one. So I don't need that one anymore. So now I can just add them together. And as long as they add up to this, I can add up the enthalpies also. So just have a careful look that I've put this down. So there's C and O, there's the 2S, there's the 2O2, and the CS2. They're all being brought down. Now here, the CO2 is over here, the 2SO2 is over here, and the C and the S are here. So they're all there. Now what can I cancel out? I've got these two. They're going to turn into a 3. That's fine. I've got 2 S's on both sides. I can get rid of those. I've got my CS2 that I will bring down. I've got carbon on both sides. I can bring my 2S over here and my C over here. Just check that that looks the same as this. And it does. So I can now add up the 393, the 593, and the 87. And that gives me minus 1075 kilojoules per mole. Okay, quite clever. It's actually even more clever, to be honest, when you're working out EMFs and ordering redox reactions, and Born-Haber cycles. So this is just a tip of the iceberg of how clever this technique really is.